This is called the enthalpy of formation. We've been looking at just the enthalpy of reactions until now, and enthalpy of formations is a little bit different because enthalpy of formation tells us what's the change in enthalpy, or what energy did it take to just make a specific single compound. So with Hess's law, we were looking at change in enthalpy within a reaction.
Wrestling, you're all dismissed.
We looked at a bunch of different mini reactions to get to our Hess's law form and the formation of delta H. But now we're going to look at the enthalpy that it takes to form 1 mole of a particular substance. In the mini reactions, there was lots of different mole ratios. There was fractions within our mole ratios. The delta HF values that were given in the appendix I gave you is just for the formation of 1 mole of that substance. That's really important, okay? So the delta HF value is just for 1 mole of your substance. The elements and the substances that are formed are all in their standard states. So if you have something that's in a different state, that will change the way that you look at things. Like, for example, let's find, they're listed in an order of their first element. Okay, so like for water, if you look under hydrogen, you'll see H2O liquid and H2O gas. So it takes a little bit of a different amount of energy to form liquid water versus gaseous water. Okay? If it has this symbol, delta HF with the little like degrees symbol or something, that tells us that it happens under standard conditions and there's nothing else we need to do. We're really not going to dive into what would take if it wasn't in standard conditions, but if we see that symbol, we know we're in the right place. So, when we solve for standard enthalpy of formation, we are going to look at the individual compounds within the chemical reaction. Okay, I want to look at a couple things here. In this reaction, we have 2 elements that are not paired with anything, right? They're just themselves. So we have plain sodium and we have hydrogen gas. Look and find those 2 in your appendix here. H2, what is its standard enthalpy of formation? It's the first row of numbers here. Do you see how up at the top there's 3 different types of values? We want the first one, okay? So what's the value for H2? 0. What's the value for like I2? 0. Or just iron, or just sodium, right? They have a standard enthalpy of formation of just 0. So if you have an element that's by itself, that means your enthalpy of formation is 0. So I gave you these values down here, okay? If you have anything by itself, it's always going to take 0 energy because there's not a reaction that had to take place, right? For H2 to form, nothing had to build that. It just bonded with itself, right? It didn't take any energy or release any energy when that happened. Okay, now we're going to look at what's the heat of formation for water as a liquid. That's different than water as a gas. Okay, and I gave it to you down here as negative 286. So when the value is given here, it's acting as though it takes 286 joules of energy to form water, right? If water was a product, its heat of formation would be negative 286. But in our case, it's a reactant. So what should we do? Flip the sign. We're going to just flip the sign. So I'm going to write there. I like to write their heat of formations underneath here. It kind of gives me a clearer picture. So this is going to be 0. I'm going to need positive 286 here. And we said that the heat of formation is just for 1 mole of the substance, right? But in this reaction, I have 2 moles of the substance. So I'm going to have to end up multiplying that by 2. Okay? Now let's look over to NaOH. Okay, remember you sort it by their first element. So you're going to look under sodium. NaOH as an aqueous is negative 470. And I keep forgetting I put it on the slide. Is it a product in this case? Right, so we can keep the sign, but what do we need to do? Multiply it by 2. Okay, so we're going to take positive 286 times 2. Gives me, let's make some room here for me.
Wait, so why is it positive?
Because since the value that's given to us in our appendix, or in this case I gave it to you right here, the value that's given here is how much it takes to form it. Okay. So when something is formed, it's got to be the product. Okay. And so if it takes 286 joules energy flowing in to form it, that means when it's broken down, it's going to release that much energy.
Okay.
Okay? So if you have to flip it, if it's a reactant side, you're always going to have to flip the sign.
Yeah.
Okay? Anytime it's a reactant in these heat of formation, you're going to have to flip the sign. Okay. So give me some room here. 286 times 2 is 572, and it's positive. And then negative 470 times 2, negative 940. Okay? And then we've got a 0 here from hydrogen gas and a 0 here from sodium. And then all we do is add them across. That's it. Right? Positive 572 minus 940. Gives me, I hope, negative 368 kilojoules. Both of them had values and not just 0. You still just add them across. Okay, so you're going to add all them together. Your book explains this in a more of like Hess's law format. It wants you to cancel a bunch of things, but it's not necessary, right? We can just look at our products and reactants here and say, well, the appendix calls it a product, but in my situation, it's a reactant, so all we need to do is flip the sign. You don't have to do mini reactions here or anything like that. You just go find the data, put it in, and then look at the mole ratio, because these numbers in the appendix are just for 1 mole of the substance, and then we plug it in from there. Much simpler than Hess's law, I think. Okay? Let's try one more. I think I've had these out of order in your slides, but let's look at one more here. Okay. With these, you do need to pay attention to the state of it, if it's a gas, liquid, or solid, because there's different, the states here are listed, so that's just something you got to be careful of. Okay, so let's find CH4 on our appendix. That is CH4 as a gas. What did you guys find? Negative 75, okay? And negative 75 would be if it's being formed, but in our case, it's a reactant, so what do we need to do? Positive 75. Okay. O2, what do we think it's going to be? 0, right? You can check yourself, but oxygen by itself should be 0, and it is. Okay. You'll see even underneath that, oxygen without O2, oxygen non as a diatomic, that has to be broken down. So that's why it requires energy. Do you see right there? If you look at your table that I gave you, O2 gas has a 0 heat of formation, but O by itself is not how oxygen is commonly found. So in order to get oxygen completely separated from itself, it had to have a reaction that took place. So that's why it required energy. Okay, now let's look at CO2.
So it only has to be flipped if it's a product?
If it's a reactant.
Okay.
Because these all assume that they're products. Right? On this table, it's assumed everything here is a product.
Okay.
So CO2 gas is negative 393.5. Is that what you guys had for that? Yeah. Okay, and then we have to look for water. H2O as a liquid. So negative 286. But what are we going to have to do to that? Multiply it by 2. Oh, I forgot my negative. And we multiply it by 2 because of this coefficient right there. Okay. The number in the table is for 1 mole of it. So in order to form 2 moles, we're going to have twice as much.
Where is it? I can't.
It's under hydrogen. So they're alphabetically. Okay, so let's see here. Negative 890.5. Is that what you guys had or no? Yeah? Okay, good. And then you'll see the unit for it is kilojoules per mole.